Students, today we are going to discuss the effective atomic number. The existence of the effective atomic number concept came from the attempts of the several scientists to find out the bonding in the coordination compounds. So, in this process or in this, we can say, regard, the Sedgwick gave Sedgwick theory and Sedgwick theory, or we can say EAN rule. Now, Sedgwick has extended the Lewis concept of the electron pair bond formation, and he also suggested that the metal ion in the coordination compound will take up electrons from the legend till it will achieve the nearest noble gas configuration, and this is called the effective atomic number rule. And the total number of the electrons that has to be given by the legend or taken by the metal ion from the legend plus the total number of electrons that was already in the metal ion, they must be equal to the next noble gas configuration. And for example, let's take this example. This is CO, then NH3 whole 6 3 plus. Here, as we know, cobalt has atomic number 27 and it has lost 3 electrons, that is the CO3 plus. So we can write it like this, 27 minus 3, that is 24. 24 electrons are there with the cobalt ion. Now there are 6 ammonia molecules. So every molecule of ammonia will going to give a pair of electrons, that is it will donate a pair, or we can say 2 electrons, means 6 into 2 means 12. 12 electrons has been given by ammonia, 6 ammonia, therefore it comes to be 36, which is the configuration of the next atom, next noble gas, that is krypton. So this is following the EAN rule. And next example which let's take is this is PTNH3 whole 5 Cl3 plus. Now here we know platinum has the number 78 and 5 and 1 6. 6 plus 2 is equal to 12. It has 86. This is a configuration of the radon. So this is atomic number of the radon. Therefore, it is also following the EAN rule. This is the EAN rule. Let me repeat it. The effective atomic number rule, which was proposed by Sedgwick, suggests that the total number of electrons which the metal atom which metal ion will gain from the ligands will make the electronic configuration of the metal which is equal to the next configuration of the next noble gas. So this is the effective atomic number rule, but it has several limitations. First one is that it has limitations. First one is that this does not explain the coordination tendency of the metal. This has no fundamental basis. And second is that many complexes are known which will not follow this rule, that is they don't follow this effective atomic number rule. And third one is that this does not say anything about the geometry of the molecule. And further, This even does not predict the type of the metal orbitals which are involved in the case of the bonding, that is whether the d orbitals or whatever orbitals that are taking up electrons. It doesn't talk about that, and it also does not explain the magnetic behavior of the complexes, means it's not talking about the number of the unpaired or the paired electrons that will be going to decide the magnetic properties. And further, this also cannot explain the that why certain molecules show more than one coordination number rule. When we say certain metals show more than one coordination number, means okay, they show different coordination number, means they gain more or less electrons from the ligand in the different complexes. So these were the limitations of the this effective atomic number rule or the Sedgwick theory. That's all for this video.